So let me remind you of something. So last class, in quotes, the class that was that I did, I talked at the very end, I talked about how to find the equation of the volume of a parallel pipe bed if we know the vectors. So like we have this kind of deal where if you have this shape here, sorry, I'm not drawing it dashed, oh well, such is life. But that's parallel pipe bed, and you know, like three of the vectors emanating from one of the vertices. So like if I call this, if I look at this one here and say that this vector here is u, and this vector here is v, and this vector here is w, you can do the magnitude of u cross v dotted with, I guess it's not magnitude, it's actually the absolute value, I apologize. It's the absolute value of u cross v dotted with w. The absolute value of that is equal to the volume of the parallel pipe bed. An interesting question that sometimes comes up is the following. Given the vertices of a parallel pipe bed, I'm going to write them out. They are -3, 9, 7, -4, 2, -1, -7, 3, 7, 6, 12, 13, 5, 5, 5, -8, -4, -1, 1, -1, 5, finally 2, 6, 13. Find the volume of the parallel pipe bed. So, kind of an annoying problem, to be perfectly frank. To figure out what we're doing here, you kind of want to, at least there's a few ways to go about this. You can kind of look for vectors that are parallel to each other. I find that to be kind of challenging. So what I typically tend to do with this sort of problem is I'm going to find every vector that emanates from one particular vertex. I know I don't need all of them, but basically here's the idea. If you look at this parallel pipe bed, this vector here that starts at this corner and ends here, that vector is u plus v. And this vector over here, that's v plus w. And u plus w, oh, sorry, I said that was u plus v, it's actually u plus, that's actually u plus w, apologize. This vector here, that's u plus v. And finally, the one starting here and ending way over here, that's u plus v plus w. The point being that if you find all 7 vectors, you can kind of identify which ones are u, v, and w, and which ones are the sums of them. So even though it's kind of a bit of work, let's do it. Now, if it were up to me, I would try to make the choice where things were as positive as possible. So I'm going to make the most negative point, which I think is this one, -8, -4, -1. I'm going to make that the vertex I start at, and every other vector is going to start there and end somewhere else. So, okay, here we go. This is a bit of work, but I think it's worth working through to kind of talk about how this works. So let's, yeah, I'm just gonna label all these points A, B, C, D, E, F, G, H. I'm gonna find every vector that starts at F and ends somewhere else. So FA is gonna be the vector, yeah, -3 minus -8, 9 minus -4, 7 minus -1. Okay. FB is going to be, we're ending at B, starting at F, so we're doing B minus F. So -4 minus -8. I should use more vectoring notation here. Sorry, little brackets, not parentheses. Apologize. So -4 minus -8, and then 2 minus -4, and then -1 minus -1 is 0. Okay, FC. So we get -7 minus -8, so 1, 3 minus -4, 7 minus -1. FD So let's see, 6 minus 8 is 14. 12 minus 4 is 16. 13 minus 1 is 14. I want to point out, just in case you think I'm insane, I've tried to find an easier way of doing this. There really isn't an easier way. You kind of really have to do this if you want to do this. So, you could get lucky and have like nicer vectors, but otherwise not really. So FE, let's see, that's going to be 5 minus 8, so 13. 5 minus 4, 5 minus 1. Okay, FG, 1 minus 8. Negative 1 minus 4 is 3, and 5 minus 1. And finally, FH. That's going to be 2 minus 8, 6 minus 4, and 13 minus 1. Okay, so now you've got your 7 terrible vectors. You are kind of, although not exactly, trying to identify the ones that are the smallest. If I looked at this whole list, I would have to guess that this is probably one of the smallest. Now, that's not for sure, but what I'm going to do is I'm going to try and find this other vectors where this one and something else adds up to that one. So like, for example, if I add this one and this one together, 460 plus 936 is 1396. And I feel like I had a 1396. I do. So I can see here that FB plus FG is equal to FE. That means FE is not one of my 3 like primary initial vectors. Let's see, what else can I see? Or what else, if you see something, say something. I see FB plus FC, right? That one plus that one gives me 5, 13, 8, which is FA. So FA is also out because FB plus FC is equal to FA. What else? Yeah. FC and FG, cool. FC plus FG. And that's equal to 10, 10, 14, which is FH. Cool. So FH is gone. All right. So we have 1, 2, 3, 4 left. So we just have to figure out which of those 4 is not the one. And it's probably this one over here. And it's probably the FD is actually the sum of all 3 of them. Because FB plus FG plus FC, 4 plus 9 plus 1 is 14. 6 plus 3 equals 7 is 16. And 0 plus 6 plus 8 is 14. So this one is also not the one. Great. So that means the 3 vectors we actually need are FB, FG, and FC. And then you can either actually do the cross product and then do the dot product, or you can just do essentially the triple determinant. You can do the determinant of those 3 vectors. So if I want to find the volume here, so yeah, the volume is going to equal, I'm going to write it as the magnitude or the absolute value, sorry, of FB cross FC and then dotted with FG. But interestingly, you can calculate this by just doing the 3x3 determinant of all 3 vectors. You don't have to do like the IJK thing, whatever. So and it shouldn't really matter which order you put them in. So I'm going to write this as the determinant of, let's see, I'll just do them in order. So FB is 460, FC is 178, and FG is 936. The nice thing about this is we happen to have a 0 in the first row, which is going to make it so we have to do a little bit less computing. But multiplying this out, we're going to get 4 times the determinant of 7836 minus 6 times the determinant of 1896 plus 0 times, it doesn't really matter, but I'm still going to write it out, the determinant of 1793. And then we do the thing. So we get, let's see, 4 times 7 times 6 minus 8 times 3 minus 6 times 1 times 6 minus 8 times 9 plus 0. So in the beginning, let's see, 4 times 42 minus 24 minus 6 times 6 minus 72. That's kind of big. So let's see, 4 times 42 minus 24 is 18. And then Yeah, I don't love this multiplication here, but fine. Minus 6 times 6 minus 72 is negative 66. So let's see, 4 times 8 is 72. 6 times 6 is 36, and 6 times 60 is 360, so 396. So we end up with 468. Yeah. And if it had been negative, we would just slap on some absolute values and make it positive. So kind of an interesting problem. It is, once you get all the vectors, you can start to see which ones are the smallest because you can see which ones they add up to. But there's not really any other way that I have found of tackling that kind of problem. So yeah, kind of neat. Yeah, let's keep going here. Sorry, my wife just sent me like a million text messages. I might want to look at them briefly. Okay. Yeah. So let's kind of move on to the next section, which is equations of lines in parametric form. Actually, I should say, before I get there, there is sorry, I keep going kind of back and forth. I should say, if you have questions about things we've covered in previous things, you're always welcome to ask. Like if you have questions about like finding the equation of a plane based on some stuff or other things we've done, you are welcome to say so. I'm going to kind of be moving forward because there's lots of stuff to cover. But if you always want me to backtrack, if you ever want me to backtrack, I'm happy to. Yeah, Madison. Oh yeah, yeah, you can totally do the So I should say more generally, cross product always is done kind of as the determinant of a 3x3 vector. Sorry, 3x3 matrix. And yes, you can always calculate the determinant of a 3x3 matrix using that other method where you do this. You write this, you write the whole matrix out. Totally right. The reason I'm showing you this way, and I'll say that in a second, then you can either copy these two columns next to it here, or you can actually copy the first two rows down here and do it that way. Either way works. And then you're going to say it's this times this times this, or sorry, this product of this plus the product of this plus the product of this. So it's going to be 4 times 7 times 6 plus 6 times 8 times 9 plus 0 times it doesn't matter minus, and then you do the opposite diagonals. So you're going to do that times that times that. And it should be 0 times 7 times 9 plus 4 times 8 times 3 plus 6 times 1 times 6. And if I didn't make any mistakes, it should turn out to be the same. Let's check. So let's see, 4 times 7 times 6 is 24 times 7 is 140 plus 128, so 168. I think. Let's see, 42, 4, yep. And then 6 times 8 times 9, good times. 72 times 6 is 420 plus 12, 432. And then 0 minus 4 times 8 times 3 is 96, and 6 times 6 is 36. And so hopefully that turns out to be 468. And it does? Yeah, it does. The reason I mentioned doing it this way is because later on, when I assume both of you will probably take 22A at some point, probably, you'll talk about vectors and matrices, and you'll talk about finding determinants of matrices. And for any larger matrix, you can't just do this thing where you do like diagonals like this. You have to do what's called cofactor expansion, where you take either a row or a column, and you take each entry in that row. So I took the 4 there, and then I crossed out the row and the column it was in, and multiplied it by the determinant of the remaining matrix. And then I went over to the next entry in the row, and I crossed out the row and the column it was in, and did the determinant of the remaining matrix. And then the same thing for the last entry, but it was a 0, so I didn't really pay attention to it. But same deal, cross out the row and the column it's in, determinant of the remaining matrix. The two things to know about this method of cofactor expansion is the sign always alternates. So it's plus this, minus this, plus this. But it also alternates, it could start on a negative sign depending on what row or column you pick. So for example, if I had decided, just while we're here, might as well say it, I could have done this in the following way. I could have said, I'm going to pick row 2 instead. If I picked row 2, then it would be -1 times the determinant of 6036 plus 7 times the determinant of 4096 minus 8 times the determinant of 4693. Basically, the sign of your term depends on whether the sum of your row and column are an odd number or an even number. So if you're starting in the 1, 1 position, 1 plus 1 is 2, 2 is even, -1 to an even power is +1. If you start here, you're in the 2, 1 position, 2 plus 1 is 3, -1 to the third is -1. So if you start, whatever position you're in determines whether you're adding it or subtracting it. And that's kind of the gist of cofactor expansion. But then when you start doing determinants like 4x4 matrices or 5x5 matrices, you start with like a row in that matrix, and then you get down to like a bunch of stuff times a bunch of 3x3 determinants, and then do it again. It's kind of terrible, and it's kind of dumb because like we have computers. Why would you do this terrible calculation that requires so much arithmetic and keeping track of things? But they will make you do it a little bit, so just be prepared. 4x4 is probably the biggest determinant you'll have to take by hand, but it could come up. Okay. Yeah, there's a lot of bookkeeping when you take 22A as far as like row reduction and finding terms of matrices. Yeah, there's also a lot of great online utilities you can use for that. So I would recommend exploring that when you take 22A. All right, let's continue on the equations of lines in parametric form. So in three-dimensional space, we don't really have a nice line equation a la y equals mx plus b. In 2 dimensions, if you describe the slope of the line, you describe the direction of the line. And in 3 dimensions, slope is not enough of a descriptor to really tell you what, like I could have a line at this slope and it could be pointing this way, or I could rotate it kind of any way, and those would be totally different lines, and they would still kind of have the same slope, for lack of a better term. So in 3 dimensions, we use parametric form. And what I'm going to point out more generally is, AKA, instead of a slope and a point, we need a direction, like a vector at the point. So in 2 dimensions, if you know the slope of a line and the point it goes through, a point it goes through, you know the equation line, or you can find the equation line. In 3 dimensions, same idea is true. If you know a point it goes through and the direction the line is going in, you know all you need to describe the line. So let's look at an example. Let's say we have this line here, and it goes to the points 5, 1, 3 and 6, 5, 1. Typically, the way we do this is we say, I'm going to imagine describing this line by a point on it at time t. So there is some particle, and at time equals 0, it's going to be right there. And then it's easiest to pick, although you can really pick any number you want. 1 second later, at time equals 1, the particle is right there at the other point we have. So how am I going to describe this using parametric equations? Well, I'm going to think of this as, at time equals 0, I want to get the point 5, 1, 3. So I know I'm going to have x equal to 5 plus something, y equal to 1 plus something, and z equal to 3 plus something. And the something is going to be how much they move over in 1 second. So in 1 second, the x coordinate increases by 1. So I want to have a 1 times t. Because when t is 0, x will be 5, and when t is 1, x will be 6. And the y coordinate increases by 4 in 1 second. So I'm going to have a 4 times t. And then the z coordinate is going to decrease by 2. So I'm going to have a plus -2 times t, which I would probably just write as -2t. And then, so this is our parametric equation for the line. And we can also note that t is any real number. So you can totally find other points by picking other values. For example, if we set t equal to 2 over here, well, if t equals 2, I'm going to get 5 plus 2 for x, and 1 plus 8 for y, and 3 minus 4 for z. And that way I can see that I've described any point on the line. You can pick weird way. You can pick any real number. I'm speaking nice integer values. This is certainly one way of writing it. You will see a couple of different ways. You might see someone write this as x of t, y of t, z of t to be more explicit about the functional relationship here. But honestly, the way we're probably going to get used to writing this is saying it as a vector. We're going to say that r of t, the position of the particle at time t, and we use r for position, is going to be equal to the initial point, 5, 1, 3. It's usually written as a point, even though we're talking about a vector, plus t times the vector 1, 4, negative 2. So there's your initial point. And here is your, I'm going to say something that's not 100% correct, but it's correct enough. There's our direction vector. Why is it not 100% correct? Because it's not a unit vector, but who really cares? It's still telling us the direction that the line is pointing in, even though it's not a unit vector. Yeah. So there's probably, like, as with a lot of vector things, 2 or 3 perfectly good ways of writing this. You can write it like this. You can write it like this. You could use vertical vectors as opposed to like horizontal looking ones. So if you really wanted to, you could write it like this. 5, 1, 3 plus t times 1, 4, negative 2. Anything goes, really. As long as you and your instructor agree on what you're doing, whatever works is whatever works. Yeah. So lines, we need a point and a direction. Great. Let's look at some more things we can do with this. So let's look at this. Where does the line, and typically for lines, we just give them like a capital L, like so say L1 or L2 or just L. The line given by the following parametric equations: x equals 1 plus 2t, y equals -1, z equals t. Where does this line intersect the plane 2x plus y minus z equal to 5? So, good question. Here's our plane. The answer could be nowhere, right? It's possible that someone is giving us a line that is parallel to the plane. Or more, I should say more specifically, giving us a line that is wholly contained in a plane that is parallel to the plane that we have. But probably not. So where does this thing go through there? Good question. Well, at this point of potential intersection, x, y, and z have to satisfy the equation of the plane. So I'm just going to plug those into the plane equation and solve for t. And if I get no solution, then I'll know that they don't intersect. So I'm going to take my equation, 2x plus y minus z equal to 5. I'm just going to substitute in x equal to 1 plus 2t, and y equal to -1, and z equal to t. So I'm going to get 2 times 1 plus 2t plus -1 minus t equal to 5. Now, the way this canonical solution is like all the t's canceled and it got like 3 equal to 5, well, then there would be no solution. But that's not going to happen here. Multiplying this out, I've got 2 plus 4t minus 1 minus t equals 5. So let's see, I've got 3t plus 1 equals 5. So 3t equals 4 and t equals 4/3. Now, although we've found that they do intersect, we haven't actually yet found the point of intersection. So we need to go back and plug this into the x, y, and z equations to figure out what the coordinate actually is. So x is going to equal 1 plus 2 times 4/3, which is 11/3. Y is going to be -1, and z is going to equal 4/3. So the point is 11/3, -1, 4/3. So they intersect. Lines in space are kind of neat. They can do a few things. So in two-dimensional space, you kind of only have a couple options. Two-dimensional space lines can either intersect or be parallel, or I guess they can be the same, right? We can say they coincide. The lines in three-dimensional space have a third option. And either intersect, be parallel, or be skew. And of course, they can also coincide, but people don't use it like that. So intersect, typically, right? They cross in one point. Parallel just means, right, they have this. So parallel is what I would say is they have the same direction. Just like in 2 dimensions, parallel lines have the same slope. In 3 dimensions, parallel lines have the same direction, and they just don't touch each other. And then skew lines don't intersect, but are not parallel. The way I kind of think about skew lines is they live in parallel planes. So like, for example, in the classroom here, this line right here in the carpet and this line right here on the ceiling definitely never intersect each other. They're definitely not parallel. They are skew. They live in parallel planes. So I often draw this as like having 2 parallel planes. And then like one line is going this way. And another line is going some other wonky direction that is definitely not parallel. Those are skew lines. Great, easy to kind of see what they are, somewhat more challenging to identify what you have based on given equations. So let's go ahead and start with this example. So here's line 1. It is given by the parametric equations x1 equal to 3 plus 2t, y1 equal to -1 plus 4t, and z1 equal to 2 minus t. Line 2 is given by x2 equal to 1 plus 4s, y2 equal to 1 plus 2s, and z2 equal to -3 plus 4s. When you're trying to find 2 lines intersect or a parallel or a skew, the parameter that you're using for each line needs to be different. So if I'm using t's for this first line, I have to use some other letter for the other line. Otherwise, it's not going to work out when I try and solve this. So basically, the idea, well, actually, first of all, let's point out they're not parallel. And we can see that because the direction for line 1 is 2, 4, -1. And for line 2 is 4, 2, 4. The directions are just the coefficients of the variables for each of the x, y, and z components. And right, not the same direction or not multiples of each other, so not parallel. So to see if they intersect, we start setting things equal to each other. So the idea basically is first we're going to set the x's to equal to each other and solve for t in terms of s or s in terms of t. So if we set x1 equal to x2, we get 3 plus 2t equal to 1 plus 4s. And I don't know which is going to be easier to solve for, probably t. So subtract 3, 2t equals -2 plus 4s, divided by 2, t equals -1 plus 2s. And then we're going to do the same thing for the y's and then plug this in to get a candidate for t and for s. So we set y1 equal to y2. We're going to get, let's see, -1 plus 4t equal to 1 plus 2s. And again, we're going to solve for, it doesn't really matter here because we're going to plug in this in. I feel like it makes sense just to plug this in right away, to be perfectly honest. So let's plug this in. And we're going to get -1 plus 4 times -1 plus 2s equal to 1 plus 2s. And solving this out, -1 minus 4 plus 8s equals 1 plus 2s. So 6s equals 6. So s equals 1, which means then t equals -1 plus 2, which is also 1. How boring. Okay, but then the test. So you've got t equals 1, you've got s equals 1. That means whatever x, whatever, if you plug in t equals 1, you get x equals 5, or x1 equals 5, x2 equals 5. You plug in t equals 1, s equals 1, you get y1 equals 3 and y2 equals 3. But then you have to check here and see, does it actually work for the z values? So plug in for z's, plug in t equal to 1 and s equal to 1 for the z equations. And let's see what we get. So z1 is going to be 2 minus 1, which is 1. And z2 is going to be -3 plus 4 times 1, which is also 1. Checks out. So that means they do intersect. They intersect at, let's see, so if I plugged in 1 for t and 1 for s, or just 1 for t, I guess, really, I get 5, 3, 1. Cool. So that is the point at which these lines intersect. So if the z equation hadn't worked out here, like if I had gotten t equals 1, s equals 1, and then plugged in those two for the different z equations and gotten different values, we would say that the lines didn't intersect, which would mean they had to be skewed. Because we already knew they weren't parallel. And I suppose we should look at an example that's probably going to end up being that way. So actually, let's look at this example first. Let's say our equation was the following. L1 is given by x1 equal to 5 plus 2t, y1 equal to 1 minus t, z1 equal to 3t. I do recommend writing them in different colors. I feel like it helps me keep track of things. Line 2 is given by x2 equal to -1 plus 4t. Y2 is given by 7 minus 2t. Z2 is given by 1 plus 6t. And it's always easy to kind of forget about checking if they're parallel to each other. But if we check, we can see that the direction for line 1, I'm going to call V1, is 2, -1, 3. And the direction for line 2 is 4, -2, 6. And since V1 and V2 are multiples of each other, right? V2 is literally 2 times V1. That means they're parallel. Parallel never feels very exciting. In a similar way, you can see the planes are parallel to each other if all of the components are multiples of the corresponding components in the other plane equation. Same kind of idea. And then thirdly, the example that's going to turn out to be skewed, but we should still check it. So our first line is given by x1 equal to 3 plus 2t. I guess I should back up 1 second here. How do I know these lines are not the same line? That's a fair question, actually. How do I know they're not this? How would I know they're not the same line? Well, I guess I could check to see if they contain the same point or not. So what I would do, check if they're the same or not, is I would plug in like, I would pick something easy like t equal to 0. Oh, I did the thing that I said I shouldn't do. I mean, it's not that bad. You should be careful. I knew these were going to be parallel, so I used t in both cases here. But whatever. So how do I know they're not the same line? Well, if I plug in t equal to 0 in the first equation, I get the point x comma y comma z equal to 5 comma 1 comma 0. So then, is there a value of t in the second equation that gives me that same point? And the answer is no, because to get, for example, the y coordinate to be 1, t would have to be 5 halves, which will not give me a z coordinate of 0. So it's not going to work out. I can't make it so that each of these is equal to 5, 1, and 0 for the same value of t. Right. If I try, for example, setting t equal to -1, just for, I don't like any of those choices. Sorry. T equal to, yeah, I guess 5 halves was a perfectly fine choice. 5 halves? 3. What am I thinking? 5 halves? 3. Sorry. If I set t equal to 3, I get the point -1 plus 12, 7 minus 6, and 1 plus 18. And clearly the y coordinates match up, but the others don't. So yeah, not the same. All right. So, and then this third example, we have x1 equal to 3 plus 2t, y1 equal to -1 plus 4t, z1 equal to 2 minus t. And let's say I'm going to write this kind of wrong on purpose, just so that we know what to do if we see this. So our second line is given by x2 equal to 3 plus 3t, y2 equal to 2 plus t, and z2 equal to -2 plus 2t. So someone cruelly gave me t's in all my equations, but I'm trying to see if they intersect. They're clearly not parallel, right? The direction here is 2, 4, -1. The direction here is 3, 1, 2. Well, definitely not multiple each other. So first set the x's equal to each other. But we're going to be careful. We're going to say, oh, well, I really need 3 plus 2t equal to 3 plus 3s. I have to make the second one in terms of a different variable. Cancel the 3's. T equals 3 halves s. And then go over to the y's. y1 equal to y2. I'm going to have -1 plus 4t equal to 2 plus s. I almost made a mistake. I almost said 2 plus t. And again, I don't really see any reason not to just plug in right away here. Some people like to do a little bit of solving first, but I really don't think it's necessary. So we just substitute that in right now. I'm going to get -1 plus 4 times 3 halves s equal to 2 plus s, and then 4 times 3 halves is 6. -1 plus 6s equals 2 plus s. So 5s equals -1, or sorry, +1 plus 2 is 3. So s is going to be 3 over 5. And then we plug that back in over to the previous one to get our t value. And that's going to give me t equal to 3 halves times 3 fifths. Sorry, yeah, that's right. Yeah. Which is what, 9 tenths? Okay. And then we go to the z's. The z1 is equal to 2 minus t, which is going to be 2 minus 9 tenths, which is 11 tenths. Z2 is going to be -2 plus 2s, which is -2 plus 2 times 3 fifths. It's definitely not going to equal 11 tenths. It's going to be -10 fifths plus 6 fifths, which is -4 fifths. So they're not the same. These lines are skew. Not parallel, but not intersecting. Or and, I should say and. Something I think is interesting, because I don't know, I think it is. I think it's really neat that the vector that is perpendicular to a plane, the components of it are just the coefficients of the equation of the plane. So for example, I know I talked about this in the last video, but I just think it's neat and I want to say it again. Also, I feel like it comes up a lot. So I will just point out that, for example, this plane, 2x plus 3y minus 4z equal to 7. This plane, which maybe looks like, I don't know what it actually looks like, but there's my plane. The vector that comes jutting out of it at an angle perpendicular to the plane itself, that vector definitely can be written as 2, 3, -4. What did I just think is cool? It's a little more useful when someone says, okay, well, given a plane with a normal vector, people might say normal, they might say perpendicular, they might say orthogonal, they all essentially kind of mean the same thing, of n equal to 3, -5, 7, going through the point 1, -3, 2, find the equation of the plane. And while there are actually literally a couple of good ways to do this, there's certainly an easiest way. And the easiest way is to start with this. It's kind of like, yeah, it actually is kind of like, it's kind of like the trying to solve the equation of the line using the y equals mx plus b form versus the point slope form. This is actually, I think of this as more like the y equals mx plus b form, and we're just going to plug in the point to find the b. What we're going to do is we're going to do, well, we know our coefficients are 3, -5, and 7. So we're going to say we know our equation is 3x minus 5y plus 7z equal to, I usually use d instead of b because we usually think of these as a, b, and c. And then plug in your point. So let's see, 3 times 1 minus 5 times -3 plus 7 times 2 equals d. So that's 3 plus 15 plus 14, which is 32. And that's your d value. So then the equation of your line ends up being 3x, sorry, the equation of your plane ends up being 3x minus 5y plus 7z equals 32. Not the only way of doing it, but it's definitely the most streamlined way of doing it, for sure. Yeah. All right. Yeah, we might as well. So the next place we're going to, the reason why we kind of talked about these things really is to start helping us find distance between things. So there's two specific distance formulas that I feel like come up relatively often, and I will be perfectly honest, I could never remember what they are. They just do not stick with me. I've tried to memorize. Okay, I haven't tried that hard to memorize them, but like I feel like I've done them enough that I should have been able to memorize them by now, and I can't. So I always just kind of think about what's going on. You probably might want to memorize them. I don't know. It depends on what your teacher wants you to do. So let's talk about the distance from a point to a line. I feel like this is the easier one. Yeah, at least in my brain. So let's say we have the point. Let's call it S, and it's the point 1, 2, 3. And we have the line given by the parametric equation, x equals 2 plus t, y equals 2 minus 3t, z equals 5t. It's always good to check just to be sure that the point isn't on the line, because then the distance would be 0. Usually they're not going to give you that, but it could happen. So just be sure, like if I plug in 1, 2, 3, do I like, no, if t is -1, I get 1, and then I get 2 plus, no, it doesn't work. Okay, great. So then draw a picture. My line, here's my point. And what we're going to do is we want to find any point on the line. Any point will do. The easiest choice is you just let t equal 0. If I let t equal 0, I get 2, 2, 0. So I'm going to pick the point. But I will say you can literally choose any point on the line and it will work. So the idea is we're trying to find this distance here, the perpendicular distance from the point to the line. We're typically going to draw, what we're typically going to do is we're going to draw a vector from the point we actually know to the line, to the point that is not on the line. I'll mention here, just because I'm thinking of it, this is what usually throws me off when I try and do the distance from a point to a plane, as I always try and drop a perpendicular from the point to the plane. That's the wrong way to go. You want to like draw a perpendicular up from the point you have in the plane. So I'll try to remember that when we talk about it. But like I always want, it's always very common to do, like, yeah, we just want to drop perpendicular because that's what we're trying to find. But it doesn't work that way the same. So let's draw this angle here. And I'm going to think about finding that distance in terms of a trig function. So I know I can find the length of this vector PS. And so if I think about it, I need to use sine of theta. The sine of theta will give me the length d over the magnitude of the vector PS. Now, here's what we need to know. We need to know that when you see sine of theta, we're trying to work towards getting the cross product to show up. Whereas if you see cosine of theta, you're trying to work towards getting the dot product to show up. Those are used, that's like always the process, really. Oh, sine, I want to make the cross product. So I know that the cross product of this vector and this vector is going to be the magnitude of this vector times the magnitude of this vector times sine of the angle between them times the length of the unit vector, but we're not going to worry about that. So, okay, well, I'm going to try and make that show up. So I want the magnitude of PS multiplied by both sides. Great, so now I just got that. But then I also want the magnitude, I maybe need to write this vector here. I also want this vector here. Let's call that vector V. I want the magnitude of V. Well, let's just write it into the equation before I actually say what it is. So I'm going to multiply both sides by the magnitude of V. The magnitude of V times the magnitude of PS times sine of theta equals D times the magnitude of V. I don't know why I always do it this dumb way. It just feels like it makes more sense to me. I should have just multiplied by the magnitude of V over the magnitude of V, because that's eventually what I'm trying to do anyway. For some reason, I've gotten into this habit of just multiply both sides by the same thing. But yeah, we can solve for D and say that the distance here is equal to the magnitude of V times the magnitude of PS times sine of theta, all divided by the magnitude of V. But I'll point out that the top there is just the absolute value of the magnitude. I guess it's just the magnitude of the cross product. So right there, this is the magnitude of the cross product of V and PS. So that's how we calculate the distance between a point and a line. The distance is equal to the magnitude of the cross product of the vector V and the vector PS divided by the magnitude of the vector V. And maybe I should say what some things are here. What is the vector V? I didn't write it down anywhere, but it's the vector that's going in the direction of the line. So the vector V could be, although you can make a different choice, I'm going to make the choice that the vector V is the vector 1, -3, 5. But you could pick any multiple of that, to be honest. And then the vector PS is going to be just the vector that starts at P and ends at S. So 1 - 2 is -1, 2 - 2 is 0, 3 - 0 is 3. And then to find this distance here, you would find the cross product, find this magnitude, and then divide by the magnitude of V. I would do it, but I feel like I shouldn't take more of your time than I have. So we'll continue this discussion on Friday.